Okay, we're going to go back to 14.1 here, and hopefully I'll finish up this video in this one. So it says that a walk in a graph is a sequence of vertices each linked to the next vertex by a specified edge of the graph. A path in a graph is a walk that uses no edge more than once, and a circuit in a graph is a path that begins and ends at the same vertex. Okay, so if we take a look at this example here, this is a graph that we've already used before, but problem 9, use the graph from above to determine if each sequence of vertices is a walk in the graph. Okay, so let's see. Now a walk is a sequence of vertices each linked to the next vertex by a specified edge of the graph. Okay, so if I go A to B to E to C, yeah, that'd be an example of a walk. Okay, but if I go D to E to C to A, well, C doesn't join A, right? To B, yeah, so that would not be an example of a walk. Okay, since C does not join A. Problem 10, use the graph from above to determine if each sequence of vertices is a path. Okay, so path in a graph is a walk that uses no edge more than once. Okay, so if we look at here's B to E to A to D to E to B. Okay, B to E, E to B. No, since the edge from B to E is used more than once, again, you can't use that edge BE for a second time there. Part B, B to E to A to B to C to E. Yeah, that'd be an example of a walk. Since no edge was used more than once. Okay. Problem 11, use the graph from above to determine if each sequence of vertices is a circuit in the graph. Okay, so a circuit in a graph is a path that begins and ends at the same vertex. Okay, so part A, you got A to D to E to C to B to A. Okay, so since I began and end with the same vertex, yeah, that'd be an example of a circuit. In part B, I'm going C to E to A to D. Okay, C to E to A to D. No, that would not be an example of a circuit, since the first and last vertices are different, and the first and last vertices have to be the same in order for a circuit to exist. Next definition there, a complete graph is a graph in which there is exactly one edge going from each vertex to each other vertex in the graph. Okay, so here's some examples. Determine if each graph is a complete graph. If it's not, just a quick explanation as to why it's not. Okay, so each edge is going from each vertex to each other vertex. So yeah, G1 is going to be an example of a complete graph. Okay, if I look at any vertex, I'm going to have an edge going to every other vertex. Okay. Now, G2 is not an example of a complete graph, since there is no edge going from A to C. There's also no edge going from B to D, okay, or D to B. So G2 would not be an example of a complete graph. How about G3? Well, again, each edge has to go to from each vertex to each other vertex. So A goes to B to C to D to E. B goes to C, B goes to D, B goes to A, and B goes to E. Okay, C goes to B to D to A to E. Okay, and D goes to B to C to A to E. So yeah, that would be an example of a complete graph then. Okay. Problem 13 says that there are four people in a room, and each person shakes hands exactly once with everyone else. How many handshakes take place? Okay, this is a problem that we've already seen before in section 1.3. It's an example of a complete graph. Okay, so if I lay out 4 vertices representing 4 people, and I got an edge joining a person to a person, then the question is, how many edges would I have drawn there? Well, vertex 1 is going to have 3 edges, going to 2 to 3 to 4. Vertex 2, I've already counted the one going from 2 to 1, so 2 to 3 and 2 to 4, that'd be 2, plus 3 is 5. And then vertex 3, I've already counted the one going from 1 to 2, so I have to count the one going from 3 to 4. That'd be 5 plus 1 is 6, and then vertex 4, I've already counted these 3 going from 1 and 2 and 3. Okay, so there'd be 6 handshakes that take place altogether. Problem 14 says that students from 2 schools compete in chess. Each school has a team of 4 students. Each student must play 1 game against each student on the opposing team. Draw a graph with the vertices representing the students and the edges representing the chess games. How many games must be played in the competition? Okay, so I got 4 students in one school and 4 in another school. And each person is going to play each other person from the other school exactly 1 time. So basically, I'm going to count these edges here. 1, 2, 3, 4 for A. Here's 1, 2, 3, 4 for B. 1, 2, 3, 4 for C. And 1, 2, 3, 4 for D. I would have counted all the edges there for E, F, G, and H. Okay, so 4 times 4 would be 16 games altogether. Okay. Definition: a coloring for a graph is an assignment of a color for each vertex in a way that vertices joined by an edge have different colors. Okay, so you can't have the same color if you get an edge joining 2 vertices. The chromatic number of a graph is the least number of colors needed to achieve a coloring. Okay, so problem 15 is where we want to color each graph using as few colors as possible, then determine the chromatic number of the graph. Okay, so in G1, let's see if I start with A and assign red to A, and then blue, red, blue. Since I got red and blue, I'm going to have to introduce a 3rd color there, which I guess I'll just call yellow. And since red, yellow, and blue all join F, and then F is going to have a different color there, which I've got green. Okay, so 4 colors are possible, is what I'm getting. Okay. The next one, vertex 1, I'm going to call that red. Vertex 2 joins vertex 1, so that's going to be blue. Vertex 3 joins vertex 1, so that's going to have to be and vertex 2. So I guess I'll have to use a different color. I guess I would assign that yellow. Vertex 4 joins vertex 1, vertex 2, and vertex 3, so I'm going to have to introduce a 4th color, which I'll call green. Vertex 5 joins vertex 1, vertex 2, vertex 3, and vertex 4. So I'll have to introduce the fifth color, which would be purple. And vertex 6 joins vertex 1, vertex 2, vertex 3, vertex 4, and vertex 5. So I'm going to have to introduce a sixth color, which I'll call orange. Okay, so 6 will be the chromatic number for G2. Okay, how about G3? Well, in G3, let's see here. So if I start with over here, A is red. Okay, so B is next to A. B has to be a different color. I'll use blue. And A touches D also. So D would hit. Now D does not touch B. So D could be different. D could be blue. And A does not touch C, so C could be red. A does not touch G, so G could be red. Okay, and G touches F, so again, I'm trying to use as few colors as possible. Blue for F, and then so these two are blue, and E would be red. Okay, now all 6 of these vertices join the center vertex, so I can't use blue or red. I'll have to introduce a third color, which I'll call yellow for vertex 8. So the chromatic number for G3 would be 3. Okay. G4. Okay, if I got vertex 1 is red, vertex 1 does not join vertex 2. So again, I'm looking for the least number of colors to be used. So let me use red again. Vertex 2 does not join vertex 3, or vertex 1 does not join vertex 3. So let me use red for that one. And vertex 1 joins vertex 4, so let me call that blue. Vertex 1 joins vertex 5. Vertex 5 does not join vertex 4, though, so I can use blue still. And vertex 1 joins vertex 6, so vertex 6 does not join vertex 5 or vertex 4, so I can call that one blue. So the chromatic number there for G4 would be 2 colors is what I'm getting there. Okay. Problem 16 is another problem that we've already seen before, but fitting for this section. A map of 13 countries in South America is given below. If countries sharing a common border must have different colors, what is the minimum number of colors needed to color the entire region? By the way, in this one, in G2, I forgot to mention, in general, a complete graph, which is, we've already seen a complete graph there. So that's this one. But in general, a complete graph will always have the same chromatic number that is the number of vertices in the graph. So there's 6 vertices, there's going to be a chromatic number of 6. Okay, so again, this is one that we've already done before, and it doesn't matter where you begin, okay, but most people would start at Brazil, and then they see all these countries kind of walking around Brazil, and so they can switch colors, okay, or go back and forth. So if I assign red to Brazil, and yellow, and then blue, and then I'm going to switch yellow and blue for a bit. Okay, so yellow and blue, yellow and blue. Now Ecuador could be red since Ecuador does not touch Brazil. Blue, here's yellow, okay. Okay, so I've got yellow, red. Uruguay does not touch any of these that I've already assigned colors, so let me use yellow again. Argentina, let me call that blue since Argentina does not touch Peru. and Chile does not touch Brazil, so or Ecuador, so I'll call that red. And the only one that I haven't assigned a color for yet is Paraguay, which so I got red, yellow, and blue all touching Paraguay. I'm gonna have to assign a different color for Paraguay, which would be green, okay, or whatever color you want, okay. So there's gonna be 4 colors there. Is the chromatic number. Okay. Problem 17. A map of the 8 counties in Connecticut is given below. If counties sharing a common border must have different colors, what is the minimum number of colors needed to color the entire region? Okay, so well, if I start with Litchfield, I'll assign that R for red, and then blue, and then red, and then blue. Blue can be Fairfield, since you know, I won't. Well, I've got blue for Fairfield and red for Litchfield. Now, since I got blue and red, New Haven has to be a different color, so I'll let yellow be that. Here's yellow and blue. Okay, so red is Middlesex, and then here's red, red, and blue. Okay, yellow for New London. Okay, so I'm counting 3 colors there for the chromatic number. Okay, there's a note in mathematics. The 4-color theorem states that any map in a plane can be colored using 4 colors in such a way so that regions sharing a common boundary other than a single point do not share the same color. Okay, and so we've already very briefly talked about the 4-color theorem in chapter 1 and section 1.3. So they kind of introduced the 4-color theorem here again. Okay. The homework in this section is on page 815. So be sure to look at the homework problems there in 14.1 for me when you get a chance. And in the next video, I'll begin 14.2.